Okay, here's the simulation for Lab 3. So we can see the train went on the outside track, and we can move it to the inside track. And there we have it. It has successfully switched to the inside track. We can switch it back to the outside track. And that is the simulation for Lab 3.
Here the LED connects to the 680 ohm resistor. The one end of the tactile sensor is connected to the resistor and the other connects to the positive charge, and the LED will turn on when this button sensor is clicked. Now we'll go over the wiring of the switches. Pictured here is an Atlas switch control. The green and black wires here connect to the positive and ground. The red wire controls the main line of the track. The blue wire controls the turnout of the track, and lastly the yellow wire represents the common connection. This is what the track switch connection looks like. Again, the red is mainline control, blue is turnout control, and yellow is the common connection. In this first demonstration, you will see the train running on the inner loop, and you can see the first LED turning on, indicating that the train is on the inner loop about to enter the shared track. The second LED will indicate the train has just left the shared track. In the second demonstration, you will see the train running on the outer loop. The only sensor set off indicates the train is on the outer loop about to enter the shared section of the track. These next two demonstrations will show two LEDs, with the first indicating the train is near the end of the spur or close to the outer loop near the crossing gate. The second video shows a second LED set off by the train reaching the beginning of the spur. The first demonstration of Lab 4 shows two locomotives running simultaneously, one train on the inner track and one on the outer track. The outer train is part of the critical global supply chain and will never stop running. The inner train will continue to loop around unless the outer train is approaching the shared track section. In that instance, the inner train will stop and wait to proceed until the outer train has passed through the shared track section. Working towards full automation between the two trains, we have our physical circuit built. Seen here is the circuit containing an inverter chip on the left and a JK flip-flop on the right. 1J is receiving input from the output of the inverter, which is receiving its input from the tactile switch connected to the outer track. So, whenever the train is on the outer track, about to enter the shared section, the inverter will receive input. 1K of the flip-flop is taken directly from the output of the tactile switch. The output of 1Q is headed towards the switch that determines whether the train remains on the inner loop or the outer loop. It is connected to the turnout control, so if the outer train is not near the shared section, the inner train will be able to continue and enter that section. 2J is receiving its input from the tactile switch mentioned earlier, and 2K is receiving input from the inverter. The output 2Q is connected to another circuit we will show shortly, ultimately switching the track to the mainline control for when the outer train accesses the shared section of the track. This circuit board shows the output of 2K from the JK flip-flop to the left. The red wire is bringing over that 2K signal into an Omron LY2 relay. Looking at the relay, it is connected to positive and negative on the bottom two connections. Above and going up on the left-hand side, we have the red wire acting as a switch, and the gray wire seen above. If the red wire sends a positive charge to the switch on the relay, the switch will flip, sending a signal through the gray wire to the mainline control of the track switch. The orange wire above is grounded for when the red wire is not sending any input. Now we will show the progress of the automation. In this video you will see and hear our circuit controlling the switch that determines if the train on the shared section heads to the inner or outer loop. When manually switching the tracks, you will notice the switch automatically reverting back to the chosen state. Finally, upon pressing the sensor, you can hear the switch attempting to turn control over to mainline control. Looking at the future of this project, the WunderTown Railroad will need future additions to complete the automation. Once the circuit shown in the last video can successfully flip the switch on the track, an additional inverter chip can be added to cut power to the inner loop, therefore stopping the inner track from entering the shared section at the same time as the outer train. This circuit can be added to the other side, stopping the outer train to back up into the spur. To achieve reversing direction of the train tracks, a circuit could be set up with two diodes on either side of a track section, isolating the current within. Then, a reverse relay could be added to change direction. Once power would be given back to that isolated section, the train could back up into the spur, receiving the boxcar of critical goods. The light located next to the crossing gate is set up to blink currently when the train is near that section of the spur.
This is the simulation of the automation circuit for Lab 4. The input represents the outer track junction sensor. Variable I represents the inner track's power. Variable S represents the switch state. When the outer train is at the junction, the switch is set to 1 to let it pass. And when the outer train is not at the junction, the inner train remains active and the switch changes state to let the inner train pass. And that is the simulation for the automation circuit of Lab 4. Here is the simulation for Lab 4 with the addition of the barn to supply the goods. So the train went on the outside track, so we can move it to the inside track. And back to the outside. And that is the Lab 4 simulation. This is a demonstration of the assembly simulation for Lab 4. So first we will assemble the program. And our first step is to set the position of the outer train at the junction. And we can see that register 0 now contains a 9, which sets that position of the train at the junction. And then we'll do the same for the inner train. And that is also set to 6. And then we set the outer train length and the inner train length. So 9 and 6 respectively. Then we move the outer train position to the accumulator. So we can see that the accumulator now holds a number 9. Then we subtract the outer track length from the train position. And we receive a 0. So we move to the check-in subroutine, which checks if the inner train is at the junction. So we've jumped to check-in, and we move the inner train position once again to the accumulator. And subtract the inner track length from the inner train position. So if the result is 0, we halt the inner train. And it was at 0, so the train was at the junctions, so it did give us a 0. And so we move on to the stop subroutine. And this increments the outer train position, first of all, letting it pass. And we hold the inner train at the junction. Now that we've let the outer train pass and the inner train is being held at the junction point of number 6, we jump back to the main routine. And we're going to go through that first couple of steps again. So we once again check if the outer train is at the junction. Since it isn't, we move on to check if the outer train is at its loop point. So we first move the outer track length to the accumulator. Then subtract the outer train position from the track length. Since the outer train is no longer at the junction, we do not need to loop it, so we just increment its position. Now we check if the inner train is at the loop point by moving the inner track length to the accumulator. Then subtract the inner train position. Since the inner train is still at the junction, we jump to the loop-in subroutine. And we set the inner train to position 0, which is the start of the track loop, and return to the main routine. This can be done indefinitely and concludes the demonstration of the Lab 4 assembly simulation.